Hello, my name is Chris Huxley, and I'll be the chair of today's webinar titled Whole of System Simulation of Catchment Water Quality Treatment Devices. Look, depending where you are connecting from, good morning, good day, good evening. We're really glad to have you with us. Now, although today's webinar is hosted by the Australian Water School, it truly is a global event. Here's an image which displays where all of you are located. We have over 700 attendees and also over 50 countries registered. So once again, thank you very much for taking the time to join us today. Okay, today's experts, we have Michael Barry and also Colin Roberts. Could you both please turn on your cameras?
Hi, Chris. Hi, everyone.
Hi, Michael. Hi, Colin.
Hey, Chris.
Welcome.
Thank you. Thank you. Great to be here again.
To start with, could I ask each of you just to introduce yourself? Michael, I might start with you since you're the lead presenter.
Sure. Yeah, my name's Michael. I'm based in Brisbane, Australia. My background is receiving water quality modelling. I've been in the consulting side of the business for 20 odd years, and I moved into the software side in the TUFLOW team about 5 years ago to continue development and augmentation of TUFLOW tools, and we're talking about one of those today. Thanks, Chris.
Brilliant. Thanks, Michael. And Colin. Colin will be on the question and answer. I'll also help Colin in that regard. Colin, can you please let us know who you are?
Yeah, sure. Yeah. I'm Colin Roberts. I run my company 89 Degrees in New Zealand, based in New Zealand, and I'm the TUFLOW reseller for New Zealand and the Pacific. I've been involved in the water modeling world for over 30 years, and particularly interested in how models can support catchment planning and catchment management. And so, really thrilled to see Catch arrive on the scene, and pretty grateful to be able to help bring it out to the market.
Brilliant. Thank you. I'm just going to drag across the results of the quiz that was shared at the start of the introduction there. And Michael and Colin, if you have any comments, please do share them. So let's see. The very first question was, what sector are you from? It looks like the vast majority are from consulting, 50%. Second to that would be government, 27%.
Yeah,
I think that we just said that's an expected range there.
I think so.
The next question was, I have prior catchment water quality experience. We have a rating from 1 to 10, 24% with a value of 1, up to a value of 4 for 10. From memory, 1 was I don't have any prior experience.
Yeah, 10 was a lot of experience. So it's actually pretty uniform after 1, more or less. So yeah, interesting.
The next question. All of catchment hydraulic and water quality modelling is important to me and my organisation.
Yeah, that makes sense. Yeah.
Starts out as 0 as not important through to important with the higher numbers there. So it's
so the top 3 or 4 categories from say 7 to 10, we've got more than 60%, more or less. So that makes a lot of sense to me. Yep.
Which validates why people have registered for the guess. Okay. Accurate simulation of catchment-based water quality treatment devices is important to me and my organisation. It looks like there's somewhat of a similar distribution to the previous question.
Yeah.
Good to see.
Yeah, 60% again for those top 4 or 5 or 3 or 4 categories. Yeah.
And finally, the quality of tools I have currently available to me to properly simulate catchment-based water quality treatment are, and then there's a range of answers there. Looks like a bit of a normal distribution sitting around average.
It does, yeah. Interesting. Oh, very good. Thanks everyone for filling that in. It's really interesting to get a feel for who's here and what their thoughts are.
Very good. With that, I might pass over to Michael.
All right. Well, it's lovely to be here again. It's been a while, so it's great to be back talking all things water and water modelling. Thanks everyone for coming along, particularly those who've got up early or are staying up late. It's very much appreciated. Thank you for doing so. So today we will be talking about whole of system simulation of catchment water quality, but we'll also be talking about how we do that in the context of treatment devices in the catchment. So ultimately, we're doing modelling to improve our environment, and one of those improvements is treatment devices. So we're talking a bit about how we might do that these days with some modern tools and some outcomes, and we'll talk about a few different case studies around that. So what we'll run through today is we'll talk a bit about the context, why we're here talking about this, what is whole of catchment water quality simulation, and what is simulation of pollutant treatment, or interventions as sometimes called. And that'll lead us naturally to a point of where we've come from as an industry in this space, and one or two current challenges that present themselves to our industry on an ongoing basis. And so once we've come to those challenges and realize what they are, then we'll explore those a little bit with some case study using modern approaches to simulating catchment water quality processes, but more importantly, treatment devices or intervention devices. And we'll talk through a case study of how we've done that and look at some outcomes and some fancy animations. And then we'll wrap up. So whole of catchment water quality simulation. What is it? Well, what it really is we are trying to use numerical models or numerical platforms to simulate the passage of both water and the pollutants within that water as they travel through a catchment from source to receiving waterway. So from top of catchment to bottom of catchment, we are trying to dynamically simulate surface water, subsurface water, and the pollutants and constituents that go with those water flows. That's what we're trying to do. Why? Well, in order to better manage our environment and environmental systems, we really need to understand the volume and mass fluxes, so the volume of water fluxes and the mass of pollutant fluxes. We need to understand what they are in our catchments to better manage our catchments. It seems pretty obvious, but that's what we need to do. And one of the reasons that we would need to understand those fluxes is so that we can intervene and control those fluxes or change those fluxes so that we can mitigate negative impacts of catchment change. I'm sure we're all aware of catchment change around the world through urbanisation or deforestation or other related processes. Understanding volume flows and mass fluxes of pollutants as a result of those changes is really important, so that our end goal, not always, but mostly our end goal, is the protection of downstream receiving waterways and the ecology that goes with those waterways. Not always, but often. So we really do need numerical tools that can help us robustly simulate whole of catchment water flow and pollutant flow and transport processes, so that we can start addressing these questions around how do we better manage these catchments and mitigate the impacts of largely human-derived interventions impacts. So as an example, here's a plan view. It's just a schematic view of an example catchment. And I'll put my marker on. There you go. So this is our demonstration catchment here with different land uses in it. So there's some agriculture, some forests, some rocky outcrops, bit of urbanisation, a sewage treatment plant here is in our land-based catchment. And then we have our receiving waterway running through here. And this is a lake or a creek or a river or an estuary or wherever it might be. And the idea is that when it rains, water and pollutants in that water are generated from these different areas across the whole catchment, which is these arrows. And that water and those pollutants find their way into the waterways, and then they run down through the waterways to finally add up and find themselves in the receiving waterway. And they impact the waterway, they impact the ecology of the waterway and the water quality of the waterway. And so this is the process that we're trying to understand by doing our numerical modelling, to try and quantify and understand these fluxes of volume and pollutant mass. But once we've done that, what we need to do is say, well, we understand those fluxes. What are we going to do about it? What can we do to mitigate or manage or reduce those fluxes so that environmental impacts are less from behavioural changes or land use changes that might have been occurring in the catchment? So what we'll try and do typically is then say, well, let's try and put some interventions or treatment measures in the catchment to reduce pollutant loads that are being delivered to our downstream waterways. And those sorts of devices that we talk about can be wetlands, constructed wetlands, or swales, or filter strips, or bioretention systems. There's lots of different systems that can be put in place. And that the idea of these systems is that they receive water from upstream and receive pollutants from upstream, and they remove some of those pollutants through a different range of processes, biological or otherwise. They'll mainly transmit most of the water that they receive, but they will remove pollutants. So our job, if we're trying to minimize the impact of pollutant generation and transport, is to optimize on a catchment-wide basis where these devices are and how they treat pollutants, how they best remove pollutants from our waterways and therefore our downstream receiving water bodies. And so the end goal, not always, but mostly the end goal, in my experience, is that in understanding these fluxes and in designing and implementing some interventions or treatment measures, we can most effectively and efficiently protect and rehabilitate our receiving waters. Because we don't have an infinite amount of time, we don't have an infinite amount of money to put devices in everywhere. So we need to work out where to put them and how to design them best so that we can really do the best to intercept and mitigate these pollutant fluxes that we know are occurring through our catchments. So that's what we're trying to do with treatment devices. Just going back to our previous figure where we had our catchment and our mass fluxes of both pollutants and water flowing off the land uses into the receiving waterway, our job with treatment devices is to say, well, let's try and put some treatment devices in this catchment in some locations and see what they do in terms of improvement of water quality. So just in this conceptual example, we'll say, let's put in some treatment devices where these green lines are that might intercept and reduce fluxes of pollutants or mass so that downstream of those devices, we go from yellow to green. We've gone from higher fluxes of mass to lower fluxes of mass. We've removed some of those pollutants. They stay in those treatment devices and are removed biological or otherwise. So that by the time we get to the bottom of our catchment or receiving waterway, we go from a red summation of pollutant fluxes to yellow, something a bit less. So our job, I think, as professionals or practitioners in this industry is to work out where we put these treatment devices, how we configure them, how we maintain them so that we can get the best return on our investment to reduce these pollutant fluxes through our catchment to protect our downstream waterways. And that's what we're talking about today. So that's the basic process of volume fluxes and mass fluxes through our catchments and how we would like to go about understanding the treatment of those for environmental reasons. How have we done that in the past? We have obviously used numerical tools in the past, generally speaking. And the primary approach for doing so, and it's not the sole approach, and I'm not meaning to say that's the only approach that's ever been used, but in my experience, since the mid-90s, the most common approach has been the use of lumped hydrology models to simulate water flow. And when we say lumped, we're sort of talking about bucket models where we have conceptual buckets of rainfall falling on soils, and when the soil's wet, they discharge the surface and water runs downstream, and one bucket outflow becomes the next bucket's inflow, et cetera, down the catchment. And so we can end up with a bottom of catchment prediction for water flows using this sort of lumped or bucket approach. And what we end up doing is we end up saying in our catchment, we might have 10 subcatchments, and each of those subcatchments will be a conceptual bucket, and everything within that subcatchment is averaged. We don't have any spatial resolution within those subcatchments. They are all one bucket. And they might be orders of tens of square kilometres or hundreds of square kilometres in some cases. Inside those subcatchments, we can't resolve any processes other than what's happening with the buckets, where they're overflowing and filling up. Most importantly, within those subcatchments, it's been my experience from what I've seen working in this space, is that there's no explicit simulation of water hydraulics. So the depth of water flows, the velocity with which water flows through systems, and the pathways which water takes within these subcatchments on a fine scale, like metre by metre resolution, it's largely absent. We predominantly look at lumped subcatchments where all those processes are just summarised in a volumetric outflow from a subcatchment. Not always, but mostly in my experience. Typically, these lumped models operate on daily or larger time steps. So we might have a daily model that runs for 10 years. And when we run a daily model, we therefore forfeit the ability to simulate hydraulics at a sub-daily time step. And we can't simulate processes at a fine finer time step than our model operates on. And typically they are daily waterways, but typically daily. And so when we do our hydrology, we do a subcatchment by subcatchment bucket analysis. We add up those volumes at the end and we say that's the flow coming out of our catchment. That's been the predominant approach from my point of view. Something similar applies to pollutant export predictions in these sorts of models. And again, we use the lumped subcatchment or average subcatchment approach. And what we say is, well, given the land use mix in these subcatchments, we use some weighting algorithms to come up with an end of pipe event mean concentration and dry weather concentration for each pollutant we're interested in. Once we have those concentrations, we multiply those concentrations by the lumped hydrology flow that we just got from the previous slide. And we say, well, this is the mass of pollutant coming off the subcatchment on a daily time step by getting a lumped flow multiplied by an event mean concentration. There's the mass. Again, on a daily or larger time step. And again, these are added up down the catchment. So at the bottom of the catchment, overall, we have the addition of 10 or 20 or 50 or 100 subcatchments worth of these pollutant predictions. Again, not the only approach, but certainly one that I've seen commonly used. Again, the downsides of this we've talked a little bit about, but there are some upsides, of course, in this typical approach, and that is that it's fast. We can definitely simulate tens, hundreds of years worth of hydrology and pollutant export using these sorts of approaches because they're fast. And they're pretty good at looking at over those multi-decadal timescales. They're pretty good at looking at the impacts, relative impacts of hydrologic changes and pollutant export changes as a result of broad-scale gross land use changes, for example. So over 100 years, we're going to lose this much forest, we're going to build this many houses. What broadly happens to hydrology? What broadly happens to pollutant export? And let's do it quickly. These models are pretty good for that and have been used widely and successfully. One of the downsides, and this is what we're talking about today, is that when we go for this lumped approach in our subcatchments, what we do is we lose on-ground connectivity between the detail of hydraulics, i.e. water flow pathways, and treatment interventions. So in a lumped subcatchment, we can't say this water flows through this device. All we can say is, look, we've got these devices in the subcatchment. We think they're going to remove this amount of pollutant, but we can't resolve it because we've lumped our subcatchments. So we miss that connectivity between what water flows where and into which devices. And we also, if we're simulating on a daily time step or greater, we miss some of the dynamic performance opportunities that we can get from our treatment devices. So we know that often treatment devices perform differently depending on flow rate of water coming into them. If we're simulating a daily time step, we lose that information because storms are typically sub-daily. So that dynamic removal performance of pollutants, we sort of lose if we're going to that daily time step, in addition to losing the connectivity in space between what water flows where and what devices are existing on the ground. So this is the challenge I'm talking about today, is moving from a lumped hydrology and pollutant export approach to actually try to get down to the detail of what water goes into what devices and what is the hydraulic conditions of that water when it flows into those devices, and therefore how does treatment differ? And that's what we're talking about today. So we need to attend to the spatial and temporal detail of hydraulics and treatment. That's what I think we do if we're looking at this key issue of connecting pollutant generation to pollutant treatment. And we're trying to really make sure that we're optimizing where we put our devices and how we configure our devices, simulating the detail of water hydraulics and pollutant generation hydraulics. How do we do that with modern tools that don't need those lumping or averaging assumptions? That's what we're looking at today. How are we going to do that? We're going to look at a real model, and we are going to have a look at a model that's been set up to look at this specific issue, and it is of a catchment in Australia, in Brisbane, which is where I live. In fact, the catchment, I live in the catchment that we're going to be looking at today, and it's known as Norman Creek Catchment. It drains directly to the Brisbane River, which is the main river in Brisbane, where Chris and I are based, at least. The black ring here is where we are in general terms. It's roughly a 30 square kilometre catchment, so it's not huge, and relief top to bottom is about 150 metres. But it is highly modified in terms of its land uses because it's an inner city suburb. You can't really see from here in terms of land use, but you can see there's lots and lots of roads. So there's houses and there's industry and hospitals and all those sorts of things, schools. Although there is a little bit of open space and forested, but not too much. This is the catchment in purple, sort of pink here that we're looking at today. This is where the model will be. And we're going to set up a catchment model of that. We're going to do pollutant generation and we look at pollutant treatment and see what we can do with that. And just for future reference, we'll be talking about road runoff. We'll get to that in a minute, but just so you know, for future reference, we're talking about road runoff pollutants from the motorway in this catchment versus other roads. So just for future reference, this is where the motorway is through the catchment. It's just a linear feature through the catchment like that. And all the other roads are what you saw before, just all the normal urban roads. So this is the motorway and everything else is urban roads. And we're talking about those in a minute. What could we look at in a whole of catchment water quality analysis? Well, anything really. There's so much to look at, but we have to narrow it down, obviously, for a finite time of presentation. So we're going to look at sediment loads generated from roads in this Norman Creek catchment. And we're going to look at sediment loads generated from the motorway, which I just showed you where it was, versus sediment loads generated from all other roads, everything but the motorway. That includes the urban roads we might live on with our houses, and then arterial roads, and then things like highways, but not the motorway. That's motorway and everything else. We're looking at sediment generation from those separately so we can compare and contrast those. More importantly, we're going to look at how those predictions of pollutant generation can be treated through our devices and where we should put our devices and how they perform under different hydraulic conditions, etc. Why are we bothering with roads? Well, roads really are a major source of receiving waterway pollution, not just sediments that we'll be looking at, but also a source of heavy metals that come from tire wear, brake pad wear, general engine wear, hydrocarbons, obviously dripping oil, petrol leaks, those sorts of things. So they really do contribute a lot of pollution to the environment. That's why we're looking at them today. But we will focus on sediments from the motorway, sediments from other roads, and see how they compare. How are we going to do it? We're going to use a new product, TUFLOW CATCH, and TUFLOW CATCH is an integrated catchment and receiving model. It simulates explicitly the 2D hydraulics and pollutant export and transport throughout catchments from top of catchment to bottom of catchment with no lumping assumptions. It simulates surface hydraulics and subsurface hydraulics, as well as receiving hydrodynamics in 2D or 3D, as well as pollutant generation, transport and treatment, and it's all linked. So we're not artificially linking one model with another. We can go from top of catchment right to the bottom in our tidal environment or our lake or whatever it is, all in one place without lumping or averaging assumptions. So this is getting to the whole issue we talked about before about linking water pathways with treatment devices. So we're actually simulating water pathways here on a highly resolved spatial and temporal basis. Sometimes people think, oh, it's really complicated to set these models up. I need lots of data that I can't get hold of, and it's all very difficult. It's actually not. In this particular catchment, this is an inner city catchment, so it has lots of good data available to it. So our model is a 5 meter grid size, and we have 2 soil layers, but the data we needed to build this model was all free, downloadable from the internet. Like I did it in not very long at all. I got the digital elevation model straight away. I got gridded rainfall that we can interpolate in TUFLOW and evapotranspiration. All the land use and cadastre and imperviousness data was available from the local council, as was key pipe networks, some of which are in the model. It was all there. I was actually really impressed with how much data was available and everything I needed to build this model. I didn't have to pay for any of it or go on detailed data hunts. It was just there on the internet and away I went. So it was really easy to set up. So we need to move away from thinking it's complicated to get all these data sets. It really isn't anymore. Depending on where you are, of course, in the world, understood. But in this situation, it was actually really easy. So please keep that in mind going forward. That was in terms of hydrology, in terms of water movement, the TUFLOW model there. In terms of pollutant transport, we're focusing on sediment, and we're focusing on sediment from the motorway versus other roads. So what we used to force TUFLOW CATCH was measured sediment liberation rates. And these came from experiments that we conducted at BMT in 2003, 22 years ago. And we did some experiments on different types of roads around Brisbane, motorways, and then major arterial roads, and then small minor urban roads. And we looked at pollutant liberation rates from those different types of roads under different conditions, particularly with regards to sediment. So we have used those liberation rates to force and set up TUFLOW CATCH to say, if it rains with this intensity, what sediment is liberated from every 5 meter by 5 meter grid cell in my model, and then where does that go? We haven't said, oh, this is a forested land use. What's the event mean concentration downstream? We haven't done that. We've simulated from source using experimental data. So we've been playing in this road runoff space for a while, and I'm going to show you one experiment that we conducted in 2003, actually right outside a house I used to live in. I don't live there now, but I used to live there in southern Brisbane. And this is a rainfall simulation that we did in 2003. And from this experiment, we collected a whole lot of data that I've then used to populate this TUFLOW CATCH model, that data being generation or liberation rates of sediment from roads. So again, not the event mean concentration downstream, but the liberation of sediment from these roads. So let's have a look at the animation or the video here. Okay. There's no sound. This is Wemburn Street. This is setting up. That's me wandering around, not doing very much as usual. This is downstream of the gully pit where we collected water that came from all these rainfall sprinklers on the road. This is a V-notch weir in the gully pit that we measured flow with. So the idea is that we pumped water through these sprinkler systems onto the road to simulate rainfall, and then we collected flow rates and pollutant concentrations in that gully pit downstream as the simulation went on. Now we're going to start it up. So we're running around madly, turning on all the pump, the valves and taps and things, and you should see water start to come out of the sprinklers, and it's falling directly on the road. These here are rainfall gauges. If you saw those, these are rainfall gauges here to measure the rainfall rate. And this is at 45 mils an hour. You can see water's flying across the road and then down the gutter into the gully pit where we're sampling at the bottom. And this is our sampling going on down here. And lots of people watching and taking photos because it was pretty exciting at the time. And then we ramped up from 45 mils an hour to 110 mils an hour, which just meant turning on the second tap up here, which is what these our colleagues are doing here with the extenders. That increased the flow rate. So we had more pollutants liberated. We got some more data around the extra liberation due to extra rainfall intensity, which is what we need to force TUFLOW CATCH. So we're sampling now in terms of flow and concentrations, and then we took the water and we tipped them into sample bottles, and we did that progressively throughout the experiment so we get an idea of concentration and flow with time, which is really important. And we're measuring flow against the V-notch weir to get flow rate. We did have overland flow on the grass, but we kept that away from the road for these pits here, these plates here, so it didn't interfere with the concentrations we're measuring in the gully pit. It's only road runoff that we're measuring in the gully pit. And then from left to right here, these sample bottles are early time on the left, moving through the simulation to further down in time on the right. And you can see that the color of the bottle goes from dark to light. That's because a lot of pollutants came off the road at the beginning and then less later on. So we got some really good information here about actual liberation rates of pollutants, particularly sediment from the roads. We're able to use that to populate TUFLOW CATCH that generates actual pollutant runoff and does not make average assumptions about event mean concentrations, but actually does what happens in the environment. So we use that information to populate TUFLOW CATCH. And what we did in TUFLOW CATCH, because we've done experiments on the motorway and on suburban roads, we said, let's use one fraction of sediment for the motorway and one fraction of sediment for other roads so we can track them independently and compare them to see what's going on. We track sediment release, transport, and treatment from those sources, so motorway versus other roads. And importantly, we simulated hydraulics and pollutant export explicitly on a 5 meter by 5 meter cell basis. Okay. we simulated one event for demonstration purposes here. We'd simulate a year or 2 years typically, but we've just done one event here so I can talk through some key features. We typically do multiple years. But we did add, and here's the motorway here running through, like I showed you before. We did add 3 hypothetical new treatment devices as the blue lines with pink circles. They're not there now. It's just a hypothetical example. We're not saying they should be there or shouldn't be there. It's just an example to see how we could treat road runoff from the motorway and from other roads. We didn't account for hydraulic throttling in these devices, which we assume to be wetlands. That's easily done with TUFLOW because TUFLOW is a hydraulic model. We can simulate pipes and V-notch weirs and orifice plates and all those things that are typified by wetlands. We can simulate those. I just didn't do them here for simplicity, but they can be done. So we simulated runoff directly on a 5 meter by 5 meter grid, the surface and subsurface. But in our intervention devices or our treatment devices, what we said is, well, we could say let's just have a constant treatment rate. Say, look, let's just remove 20% of pollutants that come into each device. That's not very meaningful because we know that different treatment devices behave differently in terms of their pollutant removal, depending on the hydraulic conditions of water coming into the device and the concentrations of pollutants coming into the device. So we know, for example, that water coming in relatively slowly at very high concentrations usually has a better treatment removal ratio than heaps and heaps of water coming in very quickly at low concentrations. So we know that happens. So we try and account for that in TUFLOW CATCH by setting up treatment lookup tables for each device. And the lookup tables are on the right here, and they are really just flow rate versus concentration. And each of these numbers is a removal percentage. So, for example, for a flow rate of 4 cubic meters a second coming into one of these devices, we're going to say that 20% of pollutants are removed if they come in at 1 milligram per litre, but 60% are removed if they come in at 80 milligrams per litre. These are just made up numbers. I'm not saying these are real. They're just made up an example. But what we're trying to do is say that treatment efficiency changes for a given flow rate with incoming concentration. And similarly, for a given inflowing concentration, say of 50 milligrams per litre, we know we're going to get better treatment at lower incoming flow rates compared to higher incoming flow rates. So we've accounted for that in our simulation of pollutant removal in TUFLOW CATCH. Importantly, when we look at future results, I need you to remember that this lookup table I'm showing you here was used unchanged for all 3 wetlands. All 3 wetlands use the same lookup table, but what we will see is their removal behaviours are different because the hydraulics that they were subjected to are different. So just bear in mind the same lookup table was set for all 3 wetlands. So we're going to look at some results now, some animations, remembering our catchment with the motorway running through it. What's about to come up on the next screen is 2 panes, a left pane and a right pane, left panel, right panel. The left panel will be an animation of motorway sediment runoff only, and the right panel will be an animation of sediment runoff from all other roads only. Different sediments, one from the motorways, one from all other roads, and you'll see the sediments run through the roads and through the treatment devices and whatever else. We don't have any treatment devices in place at the moment. It's just showing the difference between the motorway and all other roads in terms of their pollutant generation and transport. You'll see there's very different distributions of pollutants between those that have come off the motorway and those that have come off all other roads. And you'll also see there's some tidal action down in the Norman Creek itself where TUFLOW CATCH has that tidal simulation going in 2 dimensions. So on the left-hand side here is a zoom in on our catchment. Again, here's the motorway running through here. This side is concentrations of total suspended solids from 0 to 2.5, where 2.5 is red in milligrams per litre. And the right-hand side is exactly the same view, but it's presenting sediment generated from all other roads. Again, on the same colour scale, so you can easily compare the two. Now, if I run this animation, you'll see when it rains, we get really different distributions of sediments and concentrations from the motorway compared to all other roads. And in fact, looking at it, you can say, yeah, probably a lot more sediment load comes off the road, off the motorway compared to all other roads. Even though the motorway doesn't take up much room, the amount of pollutants that are dumped on the motorway by the high volume of traffic gives us those very high loading rates. Therefore, we get much more pollutant coming off the road, off the motorway. So this is just a screenshot here of that last time step, and it shows the high concentrations in the creek from motorway sediment, and really not very high concentrations in the same creek from all other roads. There's other bits and pieces around here, as you'd expect, perhaps from other roads, but really they are quite different. And that's because the hydraulics and the pollutant generation mechanisms are different from the motorway to the all other roads. And that's what TUFLOW CATCH is capturing. There's no lumping here. This is a 5-meter grid model, no lumping. And this is what I think we need to be doing so that we can better connect hydraulics with treatment, which is what we're going to look at right now. So let's look at only motorway concentrations now, and we'll put other roads to one side. Let's just look at the motorway concentrations because they were the highest. The figure coming up next is the left panel is concentrations untreated, which is pretty much what you just saw in the previous animation, left-hand panel for motorway runoff. The right-hand panel is going to be only motorway runoff, but treated with those interventions as per those 3 wetlands with that lookup table I showed you in terms of treatment efficiency. So I'm going to run the animations and you'll see there are differences in concentrations between the left and right panel because the right panel has interventions. Initially, they'll look similar, but they will evolve in time to be quite different. So please keep an eye on that. Here's the treatment devices, of course. On the left-hand side, these are not in place, but I've put them here just for visual reference so you can see where they are, but they're not in place on the left-hand side. They are in place on the right-hand side, and they are treating on the right-hand side. Again, we're plotting TSS or total suspended solid concentrations on this color scale here. All right, so I'll run this animation, and you'll see when it rains, comparing left with right. Left is no treatment, right is treatment. Initially, they're not too different, but then as the event unfolds, there is quite a difference between left and right. Much redder on the left than on the right. Why? Because we have treatment devices in place, and we are actually physically connecting hydraulics with treatment devices. So we're not making lumping assumptions saying, let's hope this water goes into here. We are actually simulating the connection between the two. So this is a screenshot here from that last time step. And what you can see is at these 3 locations, for example, on the right-hand side where treatment was in place, downstream of our 3 devices, if we compare that to the same locations on the left with no treatment, they are clearly very different. And that's because pollutants have been removed from our devices. So we can go one step better than that and we can stop looking at animations. They're nice to look at, but what we can look at is some actual results, some graphs of pollutant loading rates, for example. So we're going to go back and we're going to look at time series graphs of loading rates of sediment to Norman Creek. So that's downstream. Now, we can look at these loading rates because we're simulating our time step is on, 1 to 10 second time step. So we have a detailed description of loading rates coming into Norman Creek that is not lumped on a daily basis. It's actual time series of these loading rates. And we're going to look at firstly motorway loading rates and then secondly the other road loading rates. But we're going to put on both graphs, we're going to have a blue line and an orange line. The blue line is for untreated and the orange line is for treated. So we'll be able to see the difference in loading rates between the two for each of the motorway and other roads. And this is the quantitative side of things that you can use in your studies to say, actually, if we put in these intervention devices, this is the actual reduction in load we get. And this is the time series evolution of that road, of that load reduction. So this is a graph here for motorway sediments. Remember, this was the biggest mass flux for motorway sediments. Here is a loading rate on the vertical axis in kilograms per second, and the horizontal axis is time. The blue line is the loading rate from the untreated simulation, and the orange line is the loading rate from the treated simulation. Obviously, the loading rate from the treated simulation is less than the untreated. But interestingly, the beginning of the simulation here, blue and orange line up more or less, apart from this peak here, more or less pretty much the same all the way through until this second peak here. And that's when they start to diverge. Why is that? It's the same wetlands treating these sediments. So why is it different? It's different because the hydraulic conditions are different. And remember, we have our lookup table of treatment that relates hydraulic conditions and concentrations to treatment. So what we're saying is that in this initial flush of rainfall, hydraulic and concentration conditions are not conducive to removal, the way that we have these lookup tables set up. But by the time we get to the second part of our event, the hydraulic and concentration conditions are conducive to removal. And so we get removal. And this is really important because we are resolving on a very, very fine time step what's actually going on in these devices. Same thing for other roads. We have lower loading rates for the treated simulation compared to untreated, and really not much difference at the beginning of the simulation. Why? Because hydraulic and conditions are not conducive to that, but they are as the simulation goes on. So the device starts doing what it needs to do. We need to resolve these sorts of things to make sure we're getting our devices simulated properly. And that's what we're saying today. A couple more slides, not too many. Instead of presenting instantaneous loading rates in kilograms per second, what we're going to present now is cumulative sediment loads in tons to Norman Creek from motorways and other roads again. Same lines, blue and orange, treated and untreated, but we're not presenting instantaneous loading rates. We're presenting cumulative loads that arrive in the receiving waters over time. This is for the motorway. Again, untreated is blue and treated is orange. Time and cumulative sediment loadings on the vertical axis. You can see again that by the end of the simulation, we've removed about 0.2 tons of sediment from the motorway from our treatment devices, which is the difference between the blue and the orange line here. But again, we haven't done really very much at the beginning of the simulation because the hydraulic conditions didn't let us do it. But by the time we got through to, the sort of second end of the first day, the conditions were pretty good and the devices did their stuff. And that's why this big gap opens up between these cumulative loads between treated and untreated, because the conditions were right. Same for other roads, smaller mass loads, as we talked about. But again, this final difference here of, sort of 0.1 tons, it's really all due to the difference here after the initial flush where there wasn't much action, where the hydraulic conditions were not right. So we can look at now efficiencies of our devices. And what we've got here is just wetland 1, wetland 2, wetland 3 in these columns. And we have how they've treated motorway sediment and other road sediment. We've got entering sediment, entering and leaving, and therefore we can look at treatment efficiency. But if we look at the sediments who are entering these devices, the motorway has got almost twice as much runoff in terms of load as the other roads. Which you knew because the motorway has a whole lot more loading from lots more vehicles, which is why we're getting this. But if we look at the treatment efficiency, which is a ratio of leaving to entering mass fluxes of sediment, wetland 1 and wetland 2 are around about 65% removal efficiency. Wetland 3 is at 86%. Why is that when they had the same lookup tables for the removal of pollutants? Well, the reason is because the hydraulic conditions in wetland 3 were very different to those in wetland 1 and wetland 2. The hydraulic conditions were favourable for removal of pollutants. So as managers of our environment or modelers of environment, we should say, hey, there's something going in wetland 3 in that location. We can do really well there to remove lots of sediment load. How should we better design that wetland to capitalise on that outcome? Or how can we better design these to do better than 63 or 65%? But at least we know where to put these things and how they're performing and how they perform over the course of the duration of events. This is really important. We cannot get at this with lumping in time and lumping in space. We have to simulate these processes explicitly. So these results provide clear planning focus for us and modeling focus for us. We know what to do next now because we've got a really good idea of what devices are doing and how they're doing it. But we can only discern this because we've explicitly simulated in space and time the hydraulics and pollutant export of our catchment. We haven't used lumping assumptions, and lumping can mask this vital information. So I'm suggesting that our next steps in our industry is to do it a bit better and look at these sorts of processes in more detail instead of making lumping assumptions. Okay, last slide. Whole of catchment water quality analysis. Explicit spatial and temporal resolution is really important. If we want to meaningfully design these devices, we have to know what water goes where and what it takes with it. We can't lump anymore, and we don't need to because computers are fast. Well, GPU acceleration means we can do things fast, so we should be doing things much better than we have in the past. But we need to use appropriate modeling tools to answer the questions being asked. So again, long-term, broad-scale, lumped models for hundreds of years simulation. There's a lot to be learned from those models, and they can provide really valuable information to us as an industry. But my thoughts are that if we really want to do better with designing intervention and treatment measures on a high temporal and spatial scale, we've got to be using tools that don't make lumped assumptions. And that's what today's really been about. And with compute power increases, they're getting faster and faster every day, GPUs, thanks to our gaming friends. We can continue down this path, I think, as much as we need to. But don't take my word for it. Download TUFLOW CATCH yourself. Go to our webpage, download it. You can run it for free. There's tutorial models on there. And we have a brand new tutorial model that you can follow through and run some simulations in TUFLOW CATCH and play with it yourself and see what it's like. Run some numbers, look at some results. The TUFLOW CATCH manuals online explains all the inputs and outputs and how to build things and change things, and you can run it for free. So don't take my word for it. Have a play. That's all, Chris. That's all from me.
Oh, wonderful. Thank you very much, Michael. That was a really great presentation.
Pleasure. Sorry about the grainy footage in the 2003 video.
Looking at a younger Michael Barry.
That's right. I had hair, I think. I'm not sure.
Just a little bit. Look, the question and answer line has been running hot, and cool. Cole and I have been very busy answering what we could. I've been taking note of some questions that I thought might prompt some discussion or could be fleshed out a little bit further. So I'll just run through what I have here. Okay. One was, is there the capability to simulate different kinds of pollutants, total nitrogen, total phosphorus, gross pollutants, along with custom curves for pollutant load by land use? For example, a natural environment will have a very different TN concentration in runoff. Or TN concentration, from an urban setting versus a farm.
Yeah, 100%. So I chose sediment, but to be honest, TUFLOW CATCH doesn't even care what is simulated. You can call the pollutants whatever you like. The key is that you give those pollutants their unique and characteristic pollutant generation properties on a cell by cell or land use by land use basis. So we have models where we simulate ammonium and nitrate and phosphorus and organic carbon. We just give them different properties for their pollutant generation, and TUFLOW CATCH takes care of the rest. So absolutely, you can do those different properties on a land use by land use basis. But I will say that, again, in my experience in the past, that land use basis has been the key differentiator between assigning the event mean concentrations downstream. So a forested land use has a different event mean concentration to urban, for nitrogen, say. But you don't have to do that in TUFLOW CATCH. You don't have to say this land use is this concentration or this behavior, this land use is this pollutant export behavior. You don't have to say that. You can just say this area has this behavior and this area has this behavior regardless of the land use. So for example, you might have two grassed areas that are both grass or the same land use, but you might know locally that one of those grassed areas has had unreasonable fertilizer application to it for some reason. Maybe it's a school or I don't know what, but somebody's been putting lots of fertilizer on there that you know about. So you know that the nitrogen pollutant export properties of that grassed area are different to the other grassed area that doesn't have that application going on. So you're not limited to saying grassed area equals this properties. You just say this area has these properties and this area has this properties. If they're the same land use, fine, doesn't matter, but I have that flexibility down to my 5 meter by 5 meter cell basis to specify that, and it doesn't matter. So simulate whatever you like as long as you have those pollutant generation properties, and you don't have to be restricted by land use characterization for those properties.
That answer actually leads on really nicely to some other questions that people made. I'm going to combine two of the questions here. One was, look, are there standard liberation rates for different pollutants that have been developed for different land uses?
Yep.
And then there was another question was, are those liberation rates based on empirical equations or mechanistic models? What's your knowledge of that aspect?
Yeah. So certainly there are experimental data sets around. Our data set's one of them, and I showed you some the movie was of experimental data, and we did sediment and nutrients and metals, heavy metals. We have all those liberation rates. If you look in the TUFLOW CATCH manual, which is online, we have gone through a literature survey and we've presented liberation rates for commonly simulated pollutants for urban and forested environments. And whilst I just said we don't have to delineate by land use, we have in the manual because that's what people are used to seeing. That's for a whole range of pollutants. We've gone through and done that for people. And we think we've covered the majority of the common pollutants that will be used for those two land uses. They can be easily modified if you have more literature data. It's totally up to the user. But their initial guide is what we think might be those liberation rates for different different pollutants in the catchment. I will say that those rates are provided for one of our methods of pollutant generation we offer, which is a wash-off method. So it's accumulation and wash-off. And that's well suited to road runoff and agricultural areas and urban areas because pollutants do build up over time and then they wash off when it rains. But the other method we offer is just a shear generation, which is just sediment transport based shear generation. So depending on water velocity, which we obviously simulate because we simulate hydraulics, depending on velocity, different sediments can be eroded, like in gullies and things like that. So if you know you've got a gully of high erosivity, you can parameterize that with fairly standard sediment transport parameters, is what I'm saying. So the other model allows you to draw on a vast body of literature to get that sediment erosion rate going using meta equations and things like that. It's really straightforward to do. There's a whole body of literature out there beyond this wash-off measure we talked about.
Oh, brilliant. I mean, you presented one little package of work that was a field study. Guessing, there's a large body of work out of there from various universities that
there is
shows different changes in concentrations and different pollutants. Yeah.
The key thing there is first flush. People talk about first flush, and that's an initial pulse of high concentrations that come off roads. There's been a lot of literature about that. So if you're searching in the literature, look for first flush, and you should come up with some pretty good papers and data.
I think it also was mentioning, Chris, that obviously people can still conduct experiments themselves. It's information. I mean, hopefully it'll, once you start using the model, it often raises the question that you need to collect some more site-specific information. So that's good.
Yeah, totally.
And as an industry, the more data we have, the more the whole, industry as a whole moves forward and evolves to high accuracy.
Yeah, more robustness in the parameterization of our models. Yeah.
If we do consider that first flush as being of primary importance, when it comes to the treatment devices in TUFLOW CATCH, does it allow for a high flow bypass, low flow bypass approach? Yes.
Yeah. You can configure it any way you like because we resolve the two-dimensional bathymetry of these wetlands. If they're wetlands, we also allow for simulation of pipe networks, so we can have those sorts of features in our treatment devices directly. We're not making assumptions about it. We actually simulate the hydraulics inside these wetlands. And for TUFLOW users out there, we can do it through SGS and other measures. Not going to go into that now, but people who know what SGS is know what it is.
Okay.
There was one question there, Chris, that just tied in with that. Somebody was asking, could the model be used to assess the sediment accumulation over time in a treatment train for maintenance purposes, and having the hydraulics correctly represented and by high flow bypasses and stuff is critical for that. But
it is. So when we simulate any pollutant, we allow for them to settle. We allow specification of settling velocity and also critical settling shear. So if the shear, which is computed because we do hydraulics, is greater than a certain number, then we won't have settling or resuspension. that can be set by the user. And so what TUFLOW CATCH actually does is it accumulates sediments that have been washed off elsewhere in areas of low flow. And they will accumulate in ponds or forebays for wetlands and things like that. And you can look at that build up. It's reported as an output. And you can look at where sediments accumulating and where it's being eroded from, and look at your whole of catchment in that regard as well. So absolutely, it's a core output.
Brilliant. Someone's asked a question, Michael, that actually matches the question I asked you the other day, where you educated me on different pollutant sources. Very good question, whoever anonymous is. The question is, could we factor in air pollution contributions separately in this type of modelling?
Yeah, that's a good question. If you, in Australian capital city or similar capital cities around the world, if you go and put a container out in your backyard or your front yard or in the street and you collect some rainfall and you send that water off to the lab, you'll find that there are nitrogen and phosphorus concentrations in that rainfall that are not zero, because we have pollutants in our atmosphere that contribute to those concentrations in rainfall. So taking account of those in TUFLOW CATCH is something we certainly need to do, because we know that that's a significant contributor of nitrogen and phosphorus to our environment. So yes, indeed, that's important and needs to be accounted for. In addition to that, we have just atmospheric fallout of nutrients, for example. So trees dropping leaves, or pollen. At the moment, the streets around my house are full of yellow pollen because that particular type of tree is blossoming, and they're full of nutrients. And they sit on the gutter, and then they decay and they get washed into the receiving waterways. We need to be accounting for that as well, and we can do that through our loading rates we specify.
Right. Okay. In terms of the treatment devices, you mentioned this quite briefly, but what sort of things can you model? So is it wetlands, bioretention, any other pollutant trap devices, or all of the above?
Yep. So we are not saying in TUFLOW CATCH that we will allow for these types of intervention devices to be simulated only. What we're saying is draw a line in GIS to say this is where the device is and this is the properties it has in terms of removal. So in theory, if you have done your simulation of your treatment devices in another package, and I'm not going to mention any, but if there were some packages you were using that simulated wetlands directly, you can take performance of those devices, and you can take that performance as a lookup table and pump it into TUFLOW CATCH. We don't care where that information's come from. What we're trying to offer is a connectivity between existing small-scale tools that do simulate these removals and a broader catchment scale tool, which is TUFLOW CATCH. So it doesn't matter what the device is. What matters is the pollutant removal characteristics of that device that you want to apply, and you can get those from wherever you like, from your previous research or modeling or whatever it is, your spreadsheets. It doesn't matter. TUFLOW CATCH doesn't care. Just pump it in and let it do its thing. That's all.
Excellent. Look, I've actually just noticed the time. I didn't intend to ask some more questions, but I'm not going to get onto those. There's been over 40 questions in total now that have gone up there. Michael, Colin, and I will go through and answer all of those after the event, and they'll be published online along with the recording, also on the Australian Water School site. So yeah, that recording will be posted on the website, also via YouTube. If you were a live attendee, you'll receive a certificate of attendance within the next 2 business days. Please remember, we've got that 1-minute short survey that'll pop up in a moment. Please complete that because it helps us plan for the future. And a heads up for what's coming on the 20th of August is the next TUFLOW sponsored webinar titled Hands-on Model Running with Automation. It's a follow-on from a previous automation webinar that Jaap van der Veld presented last year. So thank you very much all for joining us. And we look forward to catching up with you again at our next event.
Thanks, everyone.
Thank you.
It's been fun.